Hello, it's Stat135, Lecture 12. On Friday, you have Quiz 2, and there will not be sufficiency on that quiz. Last time we started Lecture 8.8. A sufficient statistic is motivated because of two reasons. The Rao-Blackwell theorem tells you that you can use a sufficient statistic to lower the MSE of an estimator. And secondly, that we can use a sufficient statistic so that we don't need all of our data to estimate a parameter. So we defined a sufficient statistic to be a sufficient statistic is a statistic whereby the conditional distribution of x1 to xn does not depend on theta. So for example, if x1 and x2 are IID Bernoulli theta, then you can see that these conditional densities that we have here do not depend on theta. The theta factors out of it. So today we're going to do the factorization theorem and the minimal sufficient statistic. Introduce some notation. X to the n means x1 to xn, y to the n means y1 to yn. The factorization theorem says that t is sufficient if and only if your likelihood factors as a function g of your statistic, of your sufficient statistic, and theta times a function h, which is a function of x1 to xn. From this, we can see that to estimate theta, whereby we find the theta that optimizes the likelihood function, that is equivalent to for a sufficient statistic, where you have a factorization like this, to optimize the function g, which is a function only of t and theta. So what that tells us is that the MLE is a function of t. So here's a good example of the factorization. So say that I have x1 to xn IID normal, and sigma is known. So applying some algebra tricks here, we can write the likelihood this way, and we have the following factorization. And you can see here that x bar is a sufficient statistic. Now, you should note that you cannot factor it. You cannot factor it by combining these two exponential terms like here. So you couldn't factor it this way here, because this is not a function of x bar and mu. It's actually a function of x bar, the sample variance, and mu. So so if of course that would then be a sufficient statistic. So that would be a two-dimensional sufficient statistic, x bar and the sample variance. But since we already have a one-dimensional one, namely x bar, why would you want to have a two-dimensional one, right? So x bar is a minimal sufficient statistic, in fact. If we allow sigma squared to be unknown, then actually we need the s squared. So in that case, x bar and x bar s squared is a sufficient statistic, and it turns out to be a minimal sufficient statistic. So what is a minimal sufficient statistic? Well, we first have to talk about partitions. So imagine that you have a partition of your outcome space, and suppose that A is the coarsest possible partition that we're going to allow. So we have letters A and B. You could make a finer partition than A, so B is a finer partition. It allows 3 different varieties of B. So we're essentially adding horizontal lines, and that's fine. So now we define an equivalence relation on our outcome space. We say that x1, xn is equivalent to y1 to yn if the likelihoods are multiples of one another for some constant c that does not depend on theta. So we're going to call this equivalence relation a likelihood partition, and this will be the coarsest partition among all sufficient statistics. So why should this be the coarsest one? Well, so under this likelihood partition, so if if x1 to xn and y1 to yn are 2 data points that are equivalent under this likelihood partition, it means that their likelihood functions are essentially the same. They may just be multiples of one another by 5 or something. But so for the purpose of estimating theta, they're going to have their peak at exactly the same theta values. So they're essentially the same. And so the likelihood partition, it's a partition of the outcome space into the classes of x1 to xn that have different likelihood curves. So this is the best partition for x1 to xn for the purpose of estimating theta. Okay, so this is going to be the coarsest partition we're going to allow, and every other partition that's finer than it is what we call a sufficient statistic. So that is, mathematically, we can say a statistic is sufficient if and only if t of x1 to xn equal t of y1 to yn implies that x1 to xn and y1 to yn are equivalent under the likelihood partition. So when we replace this implies by if and only if, we get a minimal sufficient statistic. So a statistic is minimal sufficient when we have this equivalence here. When essentially what it means is that the partition that you get from your sufficient statistic is the same as the partition you get from the likelihood partition. So let's take a look at an example. So for example, if you have x1, x2 IID Bernoulli, then here I've shown the likelihood partition. So here these are various functions of theta, and you can see that it partitions my 4 outcomes into 3 equivalence classes. And here I've shown 3 different statistics. So one, T0 is just all of our data. That's a statistic. T1 is the first value, is the first component, and T2 is the sum of x1 and x2. And so right away we can see that the partitions for T2 and the likelihood partition are the same. So we would conclude that T2 is a minimal sufficient statistic. Furthermore, T0 is a finer partition than the likelihood partition, so T0 is sufficient. However, T1 is not a finer partition than the likelihood partition. So T1 is a statistic, but it's not a sufficient statistic. And you can just go to the definition of what a sufficient statistic is to check that if you want to follow the definition. So we see that T1 of 1, 0 and T1 of 1, 1 are both 1, but 1, 0 is not in the same equivalence class as 1, 1 in the likelihood partition. As you can see, they're in different equivalence classes. Hence, T1 is not sufficient. So what I recommend you do then is to fill out this table here to test your understanding, which is sufficient, which is minimal sufficient. And so when I do that, I see here that so the likelihood partition has 1, 2, 3, 4 equivalence classes, and this is the coarses partition, and it is equivalent to T3. So T3 is a minimal sufficient, and T4 is a finer partition than the likelihood partition, so T4 is sufficient. And however, T1 and T2 are not finer partitions than the likelihood partition, so T1 and T2 are not sufficient. And as always, T0, which is all of my data, is a sufficient statistic. It's in some ways where every data point is its own equivalence class. So I hope you enjoyed this lecture, and I will see you all next time. That would be Friday. Have a great day.